The universal relay is central to substation and plant automation. It provides protection, monitoring, and control of power systems. Known as the engine for substation automation, the UR provides safe and reliable protection, monitoring, and control of power systems. The universal relay, commonly known as the UR, is a microprocessor-based device containing a central processing unit which handles multiple types of input and output signals. The UR can communicate over a local area network with a wide range of devices such as operator interfaces, a computer with programming software, or another relay. Input elements accept a variety of analog or digital signals from the field, isolate and convert the signals into logic signals which can be used by the relay. Output elements convert and isolate the logic signals generated by the relay into digital or analog signals that can be used to control field devices. The CPU module contains firmware which provides protection elements in the form of logic algorithms and programmable logic gates. The protection elements and logic gates can be combined to create a protection and control scheme customized to the user's need. The contact inputs and outputs are digital signals associated with connections to hardwired contacts. Both wet and dry contacts are supported. The virtual inputs and outputs are digital bit states stored in the status table. Virtual inputs are signals generated by the local user interface, while the virtual output status stores the results of a flex logic equation. The analog inputs and outputs are signals that are associated with transducers, such as resistance temperature detectors, or RTDs, which vary through a predetermined range. The CT and VT inputs refer to analog current transformer and voltage transformer signals used to monitor AC power lines. The UR supports 1 amp or 5 amp CTs. The remote inputs and outputs provide a means of sharing digital point state information between UR relays. The specific remote inputs reflect the status of specific remote outputs of another relay. The remote output status table can be driven by whichever operand is inserted into the remote output status table. Valid operands are the status of protection element operands, virtual outputs, or virtual inputs. The universal relay has a cyclic scan. The UR reads the inputs into an input status table, solves the logic problem through the UR flex logic equation, and then sets each output to the appropriate state in the virtual output status table. The universal relay family is built on a common modular hardware platform and is configured from the following types of functional modules: power supply, CPU, CT, VT, DSP, digital I/O modules, analog transducer I/O, inter-relay communications modules. These modules are interconnected via a high-speed data bus. The UR backplane consists of 3 high-speed data buses: the high-speed parallel data bus, which runs at 80 to 100 megabytes per second, allowing the CPU to communicate with the I/O modules; the high-speed serial communications bus, which runs at up to 10 megabits per second for data communications; and the high-speed interprocessor serial data bus, which runs at 16 megabits per second and allows the DSPs, or digital signal processors, sometimes referred to as the CT-VT modules, a separate bus to communicate to the CPU. This architecture eliminates bottlenecks when a lot of data is being transferred, resulting in high-performance communication without affecting the performance of the protection elements. This is the front view of a horizontal universal relay with the faceplate removed, showing the fronts of the modules and the 4 mounting screw slots. The modular design allows the relay to be easily upgraded or repaired by a qualified service person. The faceplate is hinged to allow easy access to the removable modules and is itself removable to allow mounting on doors with limited rear depth. There is also a removable dust cover that fits over the faceplate, which must be removed when attempting to access the keypad or the RS-232 communications port. The relay is a 4RU 19-inch rack configuration. The relay is secured to the panel cutout with the use of 4 screws supplied with the relay.
The universal relay comes in both a horizontal and vertical mounting configuration. The horizontal relay measures 19 inches across by 7 inches high. The vertical relay is 3/4 the size of the horizontal mount at 7 inches across and 13.72 inches high. The front of the universal relay consists of a dedicated LED panel, 2 additional programmable LED panels, a 2-line VFD display, and a keypad. If ordered, on the lower panels of the device will be the user programmable push-button keys. Panel 1 provides several groups of LED indicators, 4 keys, and a communications port. The reset key is used to reset any latched output LED indicator or event message once the condition has been cleared. The user keys are used by the breaker control feature. The RS-232 port is intended for connection to a PC or laptop computer. Panel 1 also includes status and event cause indicators. The status indicators include the in-service LED, which indicates that control power is applied, all monitored I/O and internal systems are OK, and the relay has been programmed. The trouble LED indicates that the relay has detected an internal problem. The test mode LED indicates that the relay is in test mode, that is, at least one contact input or contact output has been forced to a particular state. The trip LED indicates that an output selected to be a trip type has operated. This indicator always latches. The reset command must be initiated whenever a trip type output relay has operated to reset this indicator. The alarm LED indicates that an output selected to be an alarm type is currently operated. This indicator is never latched. The pickup LED indicates that an element is picked up. This indicator is never latched. The event cause indicators specify the input type that was involved in a condition detected by an element that is operated or has a latched flag waiting to be reset. The event cause indicators include the voltage LED, which indicates voltage was involved in the fault. The current LED, which indicates current was involved in the fault. The frequency LED, which indicates frequency was involved in the fault. The other LED, which indicates a composite function was involved in the fault. The phase A LED, which indicates phase A was involved in the fault. The phase B LED, which indicates phase B was involved in the fault. The phase C LED, which indicates phase C was involved in the fault. And finally, that the neutral ground LED, which indicates neutral or ground, was involved in the fault. Panels 2 and 3 provide 48 amber LED indicators whose operation is programmed by the user. Also, support for applying a customized label beside every LED is provided. User customization of LED operation is of maximum benefit in installations where languages other than English are used to communicate with operators. If you are interested in customizing the labeling of the LEDs, visit this URL and download the zip file. This file will provide you with templates and instructions for creating appropriate labeling for the LED panel. The fourth panel contains a display and a keypad. The display is a 2-line by 20-character vacuum fluorescent display. While the keypad and display are not actively being used, the display will default to defined messages. High-priority, event-driven messages will automatically override the default messages and appear on the display. Also, messages can be displayed in alternate languages. Display messages are organized into menus under the main headings, Actual Values, Settings, Commands, and Targets. The menu key is used to navigate through the main menu headings. These headings provide access to functional subgroup menus. The message arrow keys are used to navigate through the subgroup menus. The value arrow keys are used to scroll through variables in the settings programming mode to increment or decrement numerical setting values. These keys are also used to scroll through alphanumeric values in the text edit mode. Alternatively, values may be entered with the numeric keypad. The period key is used to initiate and advance to the next character in text edit mode or to enter a decimal point. The help key may be pressed at any time for context-sensitive help messages. The enter key is used to store values. Each UR can be ordered with optional large user programmable push buttons. The push buttons are designed for use by field personnel for performing selected operations such as operating breakers or locking out certain features securely and reliably. The action of each push button is completely user programmable, and they can be custom labeled with a factory-provided template. Their operations can be logged in the event recorder for accurate sequence of events retrieval. The position of each push button is stored in non-volatile memory for power failure protection. Firmware version 3.0 or higher is required to support the push button option. The learning objective of this section is to make you familiar with the functionality and design of the different types of modules that are available in the UR platform. The functional modules we will be covering are the power supply, the CPU, the CT-VT DSP, the digital I/O modules, the transducer I/O modules, and the inter-relay communication modules. The Central Processing Unit, or CPU module, is the brain of the entire UR. The CPU can always be found in slot D of the chassis. All other modules in the UR accept information from the outside world and forward it back to the CPU module. The CPU then takes all of this information, performs all of the calculations needed to protect power system devices, and then sends commands back to the other modules if required. The UR CPU is offered in one of 3 different communications configurations, A, C, and D. The A version supports 2 RS-485 network ports located on the CPU terminal block. The C version has 1 RS-485 port, 1 single fiber optic Ethernet port, and 1 network port that is used for testing purposes only. The D version of the CPU has 1 RS-485 port, 1 primary and 1 redundant fiber optic Ethernet port, and 1 network port that is to be used for testing. The relay normally uses the primary Ethernet port for communications and will only switch to the redundant port if the relay detects a problem with the primary port or connected fiber optic cable. The UR power supply modules supply power to the relay and are offered in both low-volt and high-volt configurations. The configuration should be selected to match the voltage of your station battery. The low-voltage option has an input voltage range from 24 to 48 volts DC. The high-voltage option has an input voltage range from 125 to 250 volts DC or 100 to 240 volts AC. The power supply is equipped with a Form C critical fail relay that will signal another device if any problems have been detected by the internal diagnostics of the UR. A 48-volt power source is also provided on the terminal block of the power supply module that can be used for supplying voltage to a contact input when there is no voltage available from an external source. The Digital Signal Processor Module, or DSP's function, is to convert current and voltage signals into digital measurements that can then be used by the CPU for all necessary calculations. Each DSP is split into 2 banks of 4 inputs each that can be used for either all CTs or a mixture of CTs and VTs. Each bank is dedicated to 1 power system circuit, which contains phase A, B, C, and ground inputs. There are 5 different DSP configurations available for these 2 banks. The A type contains CTs in the first bank and VTs in the second bank. The B type of DSP also contains CTs and VTs. However, the ground CT on the 4th input channel is 10 times more sensitive than the normal ground CT. The C type of DSP contains CTs in both of its banks to allow for the monitoring of 2 power system circuits. The D type of DSP also contains CTs in both of its banks. However, the ground CT on the 4th and 8th input are sensitive ground inputs. The Z type of DSP is only used in the F60 feeder management relay for applications where you are trying to detect downed conductors. Only the first bank is used for CTs in this module. The digital input-output modules are where the contact inputs and contact outputs are located in the UR. The contact inputs act as sensors to detect hardwired signals from external devices in the substation. Contact outputs are hardware switches that are used for signaling devices external to the UR, such as circuit breakers. There are three different types of contact outputs to choose from in the UR family of relays: Form C outputs, Fast Form C outputs, and Form A outputs that have the option for voltage and current supervision. Form C contact outputs relays have both the normally open and normally closed terminals of the output available to the user. These contacts can carry up to 6 amps continuously and operate in less than 8 milliseconds. The Fast Form C contact output relays are the same as the Form C, as they also have normally open and normally closed terminals available to the user. However, they operate in less than 0.6 milliseconds and have a maximum current carrying capability of only 40 milliamps. The Form A contact output relays only have the normally open terminal of the output available to the user. Form A relays can carry up to 6 amps continuously and will operate in less than 4 milliseconds. Form A contact outputs also have the option to be used with the voltage and current monitoring supervision feature. The voltage monitoring feature that is included with each Form A contact output is normally used to detect problems with the breaker trip circuitry before a trip operation is required. If a problem is detected, an alarm can then be used to signal an operator that this circuit is not healthy and may not operate if required to do so. The current monitoring feature is used to protect the contact output that it is monitoring. The maximum current a contact output can interrupt without causing damage is 100 milliamps. The current monitor does not allow the output to open if there is greater than 80 milliamps of current flowing through the contact. The digital I/O module is offered in many configurations that have different combinations of inputs and outputs. Your application will determine which configuration should be selected. The transducer input-output modules are used to receive input signals from external analog devices. These analog input signals consist of two types: resistive temperature detectors, also known as RTDs, and low current variable inputs, which are called DCMA inputs. RTDs are used to measure the temperature of devices, such as motors or generators, and then convert this temperature to a value that can be measured by the UR. DCMA inputs are low current inputs that are sent to the UR from devices such as PLCs and other relays for communications. Each Transducer IO module has 8 separate input channels that can be used for measuring DCMA and RTD values and is offered in several different configurations. Power system protection and control schemes using protection relays are based on logic. In multifunctional digital relays, hundreds or even thousands of logic elements and equations are required to make decisions about the state of the power system and to generate pre-planned responses to system events. The UR uses flex logic to allow for customization of the protection and control within the relay. Flex logic is based on Boolean algebra that allows customization through a series of equations. These equations consist of operands and operators. The operands to these equations have a logic state of 1 or 0 and can be UR inputs, outputs, or the result of any protection element. The operators perform various defined functions. Examples of these functions are AND gates, timers, and latches. Each flex logic equation evaluates the parameters within it and sets an output flag based on these parameters in a numbered register called a virtual output. The evaluation of each equation results in the virtual output being forced on and has a logic value 1, or forced off and has logic value 0. Each flex logic equation is evaluated every 2 milliseconds, regardless of the number of equations programmed into the relay. In this section, we will go over some of the basic logic gates that can be used as operators in flex logic equations. These logic gates compare all of the inputs assigned to it and then set an output that is based on the status of those inputs and the function of that particular gate. The logic gates available in the UR are the AND gate, the NAND gate, the OR gate, the NOR gate, the exclusive OR gate, and the NOT gate. In the UR flex logic, an AND gate can have as few as 2 and as many as 16 different inputs. In order for the output of the AND gate to be in the 1 or ON state, all of its inputs must also have a logic 1 as well. If any of the inputs to the AND gate is in the 0 or off state, the output to the AND gate will be 0. An OR gate can also have between 2 and 16 inputs assigned to it. If any of the inputs to the OR gate is in logic state 1, the output to the OR gate will be logic 1 as well. The only time that an OR gate will be in the logic state of 0 is when all of its inputs are in the 0 state. A NAND gate can have between 2 and 16 inputs assigned to it and has the exact opposite function as an AND gate. The only time that the output of a NAND gate will be in the logic state 0 is when all of the inputs assigned to it are in the logic state 1. For all other scenarios, the output of a NAND gate will be a 1. A NOR can have between 2 and 16 inputs assigned to it and has the exact opposite function as an OR gate. The NOR gate will always have an output of 0 if any of the inputs assigned to it are in the logic state 1. The only time that the output of a NOR gate will be in the logic state 1 is when all of its inputs are in the 0 logic state. An exclusive OR gate can have only 2 inputs. The output of the exclusive OR gate will be in the logic state 1 only when one of the inputs is in the logic 0 state and the other input is in the logic 1 state. All other combinations will cause the output of the exclusive OR gate to be the logic state 0. A NOT gate can have only one input. If the input to a NOT gate is a 1, the output of the gate will be a 0. If the input to the NOT gate is a 0, the output will be a 1. Sometimes it may be beneficial to add a delay in the execution of flex logic equations to increase flexibility. Timers can be added as an operator in flex logic equations to provide a delay of any length. A delay in an equation when changing from a 0 status to a 1 status is called a pickup delay, and a delay from a 1 status to a 0 status is called a dropout delay. The fourth rule of flex logic explains the use of timers in flex logic equations. A timer operator may only be used once for all flex logic equations. If this rule is broken, a syntax error will be declared. In the universal relay, all current and voltage inputs are connected to the DSP module. The DSP module has 8 rows of inputs on its terminal block. Each row of inputs is used for measuring one phase of current or voltage. These DSP inputs are always grouped into 2 sets of 4 rows. Each group is used for measuring the currents or voltages from one power system circuit. The first row in a DSP group measures phase A. The second row measures phase B. And the third row measures phase C. When the group is used to meter current, the fourth row measures the ground current. When the group is used to measure voltage, the fourth input is used for measuring an auxiliary voltage that can be used for synchro checking. The UR allows up to 3 DSPs to be installed in one relay, each with 2 groups of inputs. In order to distinguish between the many groups of current and voltage inputs that can be found in one UR, a 2-digit naming convention has been given to each group of inputs. The name for each group of inputs is identified first by the slot location of the DSP, followed by the location of phase A for that particular group of currents or voltage inputs. If one set of currents is connected to the first group of inputs on the DSP located in the F slot, phase A would be located on row 1 of that terminal block. Therefore, that particular group of current inputs would be named F1. If a circuit is connected to the second set of inputs on the DSP in the F slot, phase A will be located in row 5. Therefore, the name given to that particular group would be F5. All DSPs installed will follow this naming convention. We now need to explain the concept of sources. Sources are used to connect one or more groups of DSP inputs to protection elements. The DSP input groups are assigned to a source, which is then assigned to the protection elements. Each DSP installed in the UR provides 2 sources for configuring. Configuring of sources must be performed before the UR will meter voltages and currents.